in this video lecture, we want to return to the topic of combining velocities, adding or subtracting velocities. You may remember, hopefully, in week 2, we did this from the perspective of sort of common sense and also the Galilean transformation. And the central idea there was that velocities add. In other words, if you had, we did an example of, say, Bob in his spaceship, he had an escape pod. If he sets off the escape pod such that it moves away from him with velocity, here we're calling it u sub r for the rocket frame. We'll get back to that in a minute, but or just some velocity u. And then if he's moving with velocity v with respect to Alice, so again, the escape pod is moving with respect to him with velocity u, then he's moving with respect to Alice, velocity v. As far as Alice is concerned, the velocity of the escape pod that she sees in her frame of reference is v plus u. And we had other examples, of course. If you're throwing a ball or something, you can throw it with a certain velocity, and then you get on a car or a bicycle or something, and you're moving in a certain direction with an additional velocity, and then you throw the ball, say, again, the velocities add. Or if it's a car and it's going one direction and you throw it the other direction, then the velocities subtract, and so on and so forth. But very simply, the velocities either add or subtract. Now we want to analyze that in terms of Einstein's theory of relativity. And before we get into those details, let's remind ourselves about the Lorentz transformation. So I've written the two basic equations here, where the r's stand for, in this case, the rocket frame. So that's what we're going to call it this time. We could call it Bob's frame, of course. But we'll say it's the rocket frame moving with some velocity v to the right compared to Alice. And we'll say she's in the lab frame, thus the L's here. So for a given event with x and t coordinates, a space coordinate x and a time coordinate t, someplace along the x-axis here in terms of as Bob essentially looks at that event in his coordinates, then we can get Alice's coordinates of that event using the Lorentz transformation. So, want to do one quick note here. We've got a little bit of algebra, as I'm sure you've seen, and your attention may be drawn over here. So let's just take a look at this, because this is going to be helpful in a minute when we look at our situation of combining velocities. In other words, we're going to do the escape pod example again, but this time from a relativistic perspective. So note that if we have two events in the lab frame at positions x2 and x1, okay, so that's within Alice's frame. She just says, okay, this happens at position x2, and then something else happens at x1, or just the difference between two positions is x2 over here minus x1, and so that gives you the distance between x2 and x1 in the lab frame. Using the Lorentz transformation equations, we can, for x2 sub L, we can plug in this with the 2's here. Okay, so we've got gamma x2 sub r plus v times t sub 2 sub r, in other words, in the rocket frame there. So that's for the x2 sub L. We just took the equation there, put that in for x2L. And then similarly for minus x1 sub L, we plugged in the same equation. We're not doing the t equation here. We're just working with the x equation. And plug that in over here with the x1 and t1. And then we just multiplied through by gamma here. So gamma times this gives us this. And then we noted over here we have minus gamma times x1 sub r. So we brought that over here just to sort of get the x's together. And then over here we have gamma v2 sub r, the rocket frame. And then over here minus gamma vt1 sub r. And so we put the time coordinates together there. And then just simplifying some algebra here, we just said for these two terms here, let's just we've got a gamma in both of them, so we'll just bring the gamma over here and call this gamma times x2 sub r minus x1 sub r. And similarly over here, I've got a gamma there, actually a gamma v here and a gamma v here, so pull those both out, and I'm just left with t2 sub r minus t1 sub r. And then I note, well, that's our delta notation that we've used before. In other words, if I've got here x2 sub L minus x1 sub L, we'll call that delta XL, the change in x sub L in the lab frame. And here I've got the same thing, but it's delta x sub R, the change in x in the rocket frame. Just the x2 coordinate in the rocket frame minus the x1 coordinate in the rocket frame. And then in this term, I've got the same or similar thing, but for time. T2 in the rocket frame minus T1 in the rocket frame. So that's just delta TR, the difference in time between T1 and T2 in the rocket frame. Again, 1 and 2 representing two different events that we can specify in rocket coordinates, Bob's coordinates, or in Alice's lab coordinates. And then we just clean it up a little bit more. We've got a gamma here and a gamma here, so we'll bring that gamma out. I can see if you caught that. A slight mistake here. We don't want a gamma in here. We've got too many gammas in there. So it becomes, in other words, we pulled this gamma out and this gamma out to put it in front. That leaves delta x sub r plus v times delta t sub r. And then, actually, that's the final equation for that we want. So we noted that delta x sub L, really, if you just put delta x sub L here and a delta x sub r there and a delta t sub r there, it's the Lorentz transformation equation when you have a difference in the coordinates. Again, difference in the rocket frame coordinates for x, x2 minus x1 in the rocket frame, delta t sub r, t2 in the rocket frame minus t1 in the rocket frame, the difference in time in the rocket frame. And that combination there in the Lorentz transformation format will give us delta x sub L, the difference in Alice's lab coordinates between those two things. Similarly, you can do the same thing for the t equation. We're not going to do it. I leave that to you as a little exercise to practice on if you'd like. But you get delta t sub L equals gamma delta t sub r plus v over c squared delta x sub r. Now you might be asking, why? That's sort of nice, but why are we interested in this? Well, let's come back to our escape pod situation and remind ourselves what velocity is all about. Velocity is simply change in distance, the distance covered, divided by an elapsed time. And we can write that as, so it's distance covered. We'll just say distance divided by the time it takes to cover that distance. In other words, we can write this, of course, as delta x divided by delta t. The distance covered, the change in x, how far have you gone in a certain amount of time, delta t. x2 minus x1 divided by t2 minus t1. And so clearly for Bob here, in terms of the escape pod, we could write u sub r. Okay, this is the velocity that Bob is measuring for the escape pod, is simply going to be delta x sub r divided by delta t sub r. Again, those are in his coordinates. As always, Bob has his lattice of clocks, his measuring system he's using, and they're all synchronized. Alice has her lattice of synchronized clocks that she's using, and the Lorentz transformation allows us to switch back and forth between those two systems. And so now we're saying, let's look at a velocity of the escape pod in Bob's frame of reference. And clearly, using his measuring system, he's at rest as far as he's concerned. Very simple to just say, okay, how far did this escape pod, he shoots off the escape pod, measures how far did it travel in a certain amount of time, and that's the velocity he's going to get for his escape pod. Now what we'd like to find, though, is what is the velocity that Alice sees in her frame of reference for that escape pod going off. And as you might guess, since we're doing this, it's not going to simply be u sub r plus v, or v plus u sub r, whichever way you want to do that in the simpler Galilean transformation example we did before. So what we can say, though, right off the bat, is just from the basic definition that the velocity of the escape pod in Alice's frame of reference is going to be u sub L. That's just definition. And it's going to be the distance covered in her frame of reference divided by the time elapsed in her frame of reference. And now hopefully you can see why we just did this little example over here, because the Lorentz transformation allows us to have a delta XL here and a delta TL. And so now what we have to do is raise the board a little bit to give us some room, but take these equations here and put them into the equation, Alice's equation for the velocity of the escape pod, u sub L, in the lab frame of reference, her frame of reference, and see what we get for it. Okay? So we'll leave that up just a second here. Now let's just have this. I think we don't need too much room, actually, fortunately, for this. So let's rewrite this. We'll say, okay, Alice says u sub L is delta x sub L over delta t sub L. Lorentz transformation. Okay? And we know u sub r up here or remind ourselves, u sub r equals delta x sub r over delta t sub r. And that's given to us. Bob measures that for us. Bob says, hey, I measured my escape pod going off and used delta x sub r, delta t sub r, and gives us some value for that. So we know what u sub r is. Now we want to find out what that value is as far as Alice sees it. That's going to be distance covered in her frame and of the escape pod and divided by the elapsed time. So using our results from over here, and let's give us a little more room here. We'll say this equals, so u sub L equals, here's delta x sub r. So we write gamma times delta x sub r plus v delta t sub r. And this, by the way, is one of the examples where we find the Lorentz transformation is very useful, why we spent the time to actually derive it, see where it comes from. So it's not just a magic formula or anything like that. So that's delta x sub L in terms of delta x sub r, delta t sub r. And delta t sub L is gamma from this equation right here times delta t sub r plus v over c squared delta x sub r. Okay? One nice thing right away, we see the gammas cancel. So we don't have to worry about gamma here. And then you look at this and say, well, what's going on? We'd like to make it a little simpler. Well, we'd like to get u sub r in here someplace because we know what u sub r is. Bob has told us what the velocity is in terms of his measurement. Can we get something in here that involves u sub r? In fact, we can if we do this. Let's factor out a delta t sub r from each of these terms here. Okay, and rewrite this and see what we get. So remember the gammas cancel, so we don't have to worry about those anymore. So I've got delta t sub r times, well, this term then becomes delta x sub r over delta t sub r, right? This term here, delta x sub r, can be written in this form, delta t sub r times this. In the denominator here, up here, that cancels. That's just delta x sub r in a little more complicated format there. Plus the second term, we pulled the delta t sub r out here, so that's just going to be v times 1, or v. I have a great v there. Let's make it a little better. Looks a little better. Okay, so that's the numerator, the top part there. Again, all I did was pull out the delta t sub r from this term and a delta t sub r from this term and rewrote it like this. Okay, just a little bit of algebra there. Now let's do the same thing actually for the bottom denominator here, the bottom part. So we're going to pull out a delta t sub r. And this first term just becomes 1 then, because delta t sub r times 1 is delta t sub r. And then I've got the v over c squared here. That's not going to change. And I pulled out a delta t sub r from this term. So just like we did up here, this becomes delta t sub r. Oops, sorry. My mistake. Delta x sub r over delta t sub r. So just use a little algebraic trick there to pull out delta t sub r. And one thing we know right away is these delta t sub r's are going to cancel, so we get rid of those. But why did we do this? Well, look what we've got inside here. I've got a delta x sub r over delta t sub r. Another one down here, actually, delta x sub r over delta t sub r. And that is u sub r, by definition. So I can replace this and this with just the value u sub r that Bob is going to tell us. And now we'll erase this over here so we can write it nicely. So this comes up here, and what have we got? We've got, and we'll just rewrite UL here. Okay, remember this is the velocity that Alice sees of the pod, escape pod, in her reference frame. So I've got U sub L equals, on the top, this is just a U sub R, by definition, delta x sub r over delta t sub r, plus V. And on the bottom, I've got 1 plus V over c squared times u sub r. And that's my answer. Okay, now I have found, if I know how fast Bob is moving with respect to Alice, and Bob shoots off his escape pod, and he tells me how fast it's going in his frame of reference, where again, he is stationary, he's measuring it, receding away from him, going away from him, and he gives me that velocity here, then I can find out what Alice is going to measure the velocity of the escape pod as. It's going to be the velocity that Bob measures plus the velocity between reference frame velocity here, the difference in velocity between the two reference frames. And then on the bottom, 1 plus v over c squared u sub r. Sometimes we write this like this, just so, slightly different form. We obviously can do v plus u sub r plus v if you want, but we'll do that. And then on the bottom, sometimes we just write it as 1 plus u sub r v over c squared, or you could do v u sub r over c squared. It doesn't really matter there. Okay, let's look at what this is telling us. First of all, so that's our final answer. Here was our derivation. Not too difficult, hopefully. And remember where it came from. We just said, by definition, velocity is change in position divided by the elapsed time. And we just use the Lorentz transformation equations to go from Bob's frame of reference to the version in Alice's frame of reference. And again, this is what we get here. So this comes over here. Well, it sort of looks like the Galilean transformation if you think about it. Because, look at this. On the bottom, on the top, the numerator, we have ur plus v. That's just what we did normally in everyday common sense experience. Galilean experience, you could call it, I suppose. You just add the velocities. You say, Alice would say, okay, it's just going at u sub r for Bob, and then I'm just going to add the velocity to it, and that will give me the velocity that I see. Except we've got this denominator factor down here. And note what is down here. We've got a 1 plus a v over c squared factor, or ur v over c squared. Note that this factor here is going to be very small unless both v and ur are pretty close to the speed of light. Under normal circumstances, here I've got 1 plus 0.00000, a whole bunch of zeros out there, 15 or so. And therefore, in real life, even though this relativistic effect really is true, would happen if we could measure that precisely, in real life we don't notice it. This just becomes ur plus v over 1 when v, okay, the relative velocity between the two frames of reference, and u sub r, the velocity of the escape pod, or the velocity of the object in the other frame of reference, is small compared to c. So we see that this reduces to the Galilean, our normal Galilean transformation, addition of velocities, combining of velocities that way, when ur and v are non-relativistic, as we might say. In other words, not near the speed of light. Now let's look at a couple other things too, though. So that's good news. If we didn't get that, something would have been wrong, because we know in our everyday experience the Galilean transformation, addition of velocities, works. Let's also look at the case, what if u sub r equals 0? It's always good, as we've done before, to just try some simple numbers in here and see what happens. So if u sub r equals 0, notice if the velocity of the escape pod is 0 to Bob, which means he hasn't shot it off from his ship, okay, we would expect then, it's just going to be traveling along with his ship, Alice should see the velocity of the escape pod just to be v, because that's what the velocity of Bob's ship is, and if the escape pod is just stuck to the ship, its velocity has got to be v as well in terms of what Alice observed. So let's see if our equation works. U sub r equals 0. So let's plug that in here. So we'll say that leads to u sub l equals 0 plus v over 1 plus, well, if u sub r is 0, this whole thing over here becomes 0. 0 times anything is 0, of course. So it's just 1 plus 0. I get v divided by 1. That's just v. And that's exactly what we'd expect to get. Okay, so that if velocity of the pod, or whatever the object is 0, then the velocity as Alice sees it of the object is just the velocity of the difference in the frames of reference, really, the relative velocity between them. So that's one thing to check. Let's do another one here. Okay, so that checks out. What if v is 0? Okay, if v is 0, then think about what's happening here. That means Bob and Alice really are standing next to each other. Bob shoots off the escape pod. In other words, Bob is not moving with respect to Alice. They're side by side, stationary with respect to each other. If Bob shoots off the escape pod, Alice, and he sees it at velocity u sub r, well then of course Alice should see it at velocity u sub r as well. So let's see if that's what we get. If v is 0, on the top I get u sub r plus 0 all over 1 plus, and this time v, the velocity between the frames of reference is 0. They're essentially the same frame of reference. So this whole thing becomes 0 again. Again, you got 1 plus 0, and this just equals u sub r. Right? So that checks out as well. So that's good news. Now, though, let's do another case here where what happens if, let's see this. Let's let v here, let's get up to relativistic speeds and see what happens. Let's say v is 0.9 c, 9/10 the speed of light. And Bob has a super fancy escape pod as well as a super fancy ship, and he can shoot off his escape pod as he measures it at 0.7 c, 0.7 times the speed of light. So that means it's receding away from him at 7/10 the speed of light. Again, he, as far as he's concerned, he's stationary in his frame of reference. He sees the escape pod going out. So the question is, what does Alice see in terms of the velocity of the escape pod? So let's try out our formula here. So we got u sub L, the velocity in the lab frame that Alice is going to see. So u sub r is 0.7 c, plus v is 0.9 c, for example. On the bottom, we've got 1 plus u sub r, 0.7 c, times v, or the other way around if you want to do it that way, but we'll do the bottom one here, times v is 0.9 c, all over c squared. Okay? So we just put that there. So what do we have here? We'll do one more step, squeeze it in here. So 0.7 c plus 0.9 c, 1.6 c. Greater than the velocity of, let me rewrite that so it looks a little better, 1.6 c. Definitely greater than the speed of light there. What do we have on the bottom? We've got 1 plus 0.7 c times 0.9 c. So that's 0.7 times 0.9 is going to be 0.63. 9 times 7 is 63. You get the decimals in there. It's going to be 0.63, and I've got a c squared there. So I get 0.63 c squared all over c squared from there. C squareds, of course, cancel. Those cancel. And look what I'm left with over here. This equals 1.6 c all over 1.63. 1 plus just 0.63. The c squareds are gone there. So this becomes, get out your calculator and figure this out, but it's roughly, looks like 0.9 something c here. 0.9, something else there, maybe times c. The important point is not so much the exact figure there, is the fact that it is less than the speed of light. And in fact, the way this equation works is, no matter what speed you put in for u, r, and v, as long as they are less than the speed of light, then the result will always be less than the speed of light. In other words, Galileo, in our common sense, would say, hey, if I've got 0.9 c and 0.7 c for the escape pod shooting off, shouldn't Alice see the escape pod be at 1.6 times the speed of light? And intuitively, we think, well, that's the way it should work. In actual fact, it doesn't work that way. That because of the Lorentz transformation, how that works, we put this together, found out the velocity in the lab frame. We get this equation here. This equation will always give us, no matter what these two values are, again, as long as they're less than the speed of light for objects that we're dealing with, then the result will always be less than the speed of light. It adds in sort of a weird way that way. But it also shows us there's something about that ultimate speed limit that we'll talk more about actually in a video lecture coming up. We've mentioned a few times before that for whatever reason, which is sort of built in the theory here, you cannot go faster. You cannot actually get a material object up to the speed of light. It seems to be a natural speed limit in the universe. Okay, so that is our basic combining of velocity equation here. Again, we got it from the Lorentz transformation and just basic definition of a velocity. And we see the Galilean transformation is embedded in it in a sense, because if you are the escape pod velocity and the relative velocity between the frames are low with respect to the speed of light, then we just get our normal UR plus V, just add velocities. But when we get speeds up close to the speed of light, they do not add as we expect them too. So there's that. A little bit later here, another video lecture, we'll look at the case where what happens if the escape pod actually goes off to the side at a perpendicular angle, either straight up or off to the side here. So we'll deal with that as well.